Greetings, friends. Got a lecture here on dimensional analysis, which I consider to be one of the most powerful tools that a scientist could have at their disposal. I'm confident of this, that had I mastered this technique when I was a student, everything would have been easier and my grades would have been higher. So let's get started, and I think you'll see what I'm talking about. Um, So what we're not talking about is converting from one set of units to another. I mean, people use the term dimensional analysis to talk about conversion of kilometers to miles and gallons to liters. Always important to do that, but this is different. What we're going to exploit is knowledge of a physical system that we want to analyze and the units of the physical constants that are involved to get results that otherwise we would have to calculate by some laborious technique. And I'm going to show you a number of examples after I illustrate the process. Those examples range from simple mechanical systems to complex mechanical systems to atomic physics, cosmology, wide-ranging application. So you can read this at your leisure, but the idea is that we're going to use a notation that looks like this: square brackets to indicate the units associated with physical constants and measures that are appropriate to a particular problem. Okay. This yellow box indicates that as we go along, where things get a little more familiar to you, then I'll be skipping details so we can cover more examples. So let's do a mechanical system. This is the simplest mechanical system I can conjure up. It's a pendulum, a weightless bar with a mass on the end hanging from a ceiling or something that doesn't move. And let's see if we can apply dimensional analysis to the challenge of figuring out the period of such a pendulum. That is, how long does it take the pendulum to swing back and forth? And to do this, we're going to introduce a technique that we'll use over and over again, and that is to write down the key parameters that you can think of that describe this system. And I've done that here. There's the length of the pendulum, L, which has units of length, capital L. We're trying to calculate the time of oscillation, that is the period of oscillation of this thing swinging back and forth, and that period will be measured in time, capital T. We're going to put in the mass at the end, this mass, and we acknowledge that there's gravity. And the units of gravity here on anywhere, but at the surface of Earth we use G for the acceleration of gravity, and that has the units of length over time squared. I personally, now obviously this is an ideal situation. We're not going to do wind resistance or any other sophisticated minor correction. This is all about an ideal pendulum swinging in Earth's gravity. And these are the parameters I can think of that pertain. I've taught this many times to classes of students. They come up with the same list. So let's proceed. So the challenge is to arrange this group of 4 parameters so that we get units of time, because ultimately we want to estimate the period of the pendulum. So we use the length of the pendulum, the mass, and acceleration of gravity. And if you go through this, you can try it any different number of ways you want. You'll find that the only way to configure these parameters is this: the square root of the length over the acceleration of gravity. And you'll also see that mass isn't a factor. And here's the logic. We have some equation the period of the pendulum. So on the left side, we only have time. On the right side, we can use the length of the pendulum, the mass, and gravity. But since there's no mass on the left side, there can't be any mass in the equation on the right side. Otherwise, the units wouldn't balance. So right away, we see that the mass of this weight at the end of the string cannot participate in calculating the solution. Furthermore, to get units of time using L and G, this is the way to do it. If you have L over G, the length components of the dimension cancel, and we end up with time squared. There it is. And to get time, we have to take a square root. And indeed, this is the way the period of a pendulum depends on length. The absolute value for the period, where you want to put an equal sign here, we're just missing the 2 pi that you get if you actually do the physics. But this equation is powerful because if we have to estimate how the length of a pendulum influences the period, the fact that there's a 2 pi becomes irrelevant. So if we now know from this that if we double the length of the pendulum, the period goes up as the square root of 2. So that's our first little step in this process. We can do the same thing for this kind of a harmonic oscillator. So here we have a fixed structure and a weight sitting frictionless with respect to this sliding surface and a spring. So here we'd like to get the frequency of oscillation of this spring. If you pull it and let it go, it'll go back and forth. Or if you push it, it'll go back and forth. And since we've assumed no friction, it'll just keep doing that forever. So what's the frequency of that? Spring constant has units of mass over time squared. And the mass of the weight is m. And so the question is, how can you configure the spring constant and the mass, so that we estimate the frequency and come out with something very similar to the pendulum? This time the mass is involved. See, so you see the spring constant and the mass have to go into the calculation, so we get time squared. So we get that the frequency, which is in units of 1 over time, means that this, whatever we have on the right side, has to have the units of 1 over time, and the way to get that is k over m. The k has mass, and the mass of the object has units of mass, and those cancel. And so we're left with 1 over time squared, and you take the square root and you get 1 over time. And indeed, this is the frequency of an oscillator of this type. Once again, we're missing the 2 pi.